the PC axis here. I've just plotted out the first 5 eigenvectors. It's a little bit more interpretable, right? So the code that I used to create it was looks like this, right? So we've got an output data set called prin. We want to create new variables, and we're going to call those pollute 1, pollute 2, pollute 3, pollute 4, pollute 5, right? So pollute 1 is basically the values when you have projected your data onto the first eigenvalue, first eigenvector. Pollute 2 is your score on your second eigenvector, all the way up to pollute 5, right? So this is what it's doing, create an output data set called prin, short for principal components, and the variable names, the new variables will be called pollute 1 through pollute 5. So if you were to look at this data set, hopefully this will work, you would see these new variables in there, and those are the actual scores of the projections onto your new axes. Okay, so what happens when you do that? Well, I've got my eigenvectors, right? So what do the eigenvectors mean? That's what it comes down to. What does eigenvector 1 and eigenvector 2 mean? If I have a big score on eigenvector 1, what does it mean? It means, well, I have probably big scores. I want to look at those values that have big values a long way away from 0, which variables have loadings a long, long way from 0. So another way of thinking about it is which variables are highly correlated with that first axis, right? Which variables are very highly correlated with the second axis. And that is what this is telling you. This is saying, I think it's this one here, this line here is showing you, so these are all the variables. This line is describing PC axis 1, and it's saying, hey, look, precipitation is, oh, that's not, sorry, this one is PC1, I think. Yeah, component score 1. This line here is PC1, right? Precipitation is very heavily negatively correlated with PC1. So if you've got a data point that is a long, long way, gives a big positive value on PC1, then it probably has a very small precipitation score. I say precipitation, right? January temperatures is not very heavily correlated, so actually it doesn't really matter what your January temperature is. It has very little meaning with respect to PC1. January temperature, however, is highly correlated with PC2, and so on and so forth. I don't like these plots. I find them difficult to understand. I find these far more meaningful. So these, I could draw these as vectors, and that's usually what I do. In fact, that is what we will do with the movie data set. So these then are the variables with respect to PC1 and PC2, right? Sure, I can, let's look at the actual data. Here's the actual data, right? Here are the 60 data points. I don't have to have the actual individual values of mortality. I could run it without that thing. In fact, oh no, I won't do it. But what have I got? I've got values of, this is PC1 and PC2, right? So I know that big values in PC1, if I'm looking at the plot and I'm going in this direction, what does that mean with reference to the original variables? Well, I can simply look at this plot here and say, well, which variables are correlated in this, which vectors are pointing in this direction? Oh, that's sorry, that's the wrong one. That's 2 and 3. I was wondering what January temperature is there. Here's 1 and 2, right? So this you can see. Oh, damn it. There we go. Thank you. Okay, so we know that as in our PC1 versus PC2 of the data, we know that as we move along points that are in this direction, they're going to have big values for housing and education, right? They're going to have very low values of these variables that point in this direction, right? Now remember January temperature, that doesn't have a big correlation with respect to PC1, but it was highly correlated with PC2, right? So scores that were high in PC2, right, or points that are up here have high January temperature values, right? So let's go back to the point. We can assume then that points that were up in this direction have high January temperature values, right? Points in this direction here had high housing values and those other things, right? So what we really want, I would argue, is to overlay the vectors describing the original variables onto this plot. And that would give it context, right? So we want to know, well, okay, this is a plot of a two-dimensional representation of my 15-dimensional data space, right? We can say, hey, look, the amount of variation that this plot explains is 48%. The first axis, 30%. The second one, about 18%, right? So obviously we've lost some information there. But what does it mean? I need to then understand what's going on. Okay, so I would argue that the best kind of plot, or a very common, you'll find is a very common plot, actually is a combination of this, which is a description of how the variables relate to the PCs and the data. Right? Oops, component 1 versus component 2. That's called a biplot. Right? Because then you can see, basically, here is my representation of the data plan. Okay, and then you look at the vectors describing the original variables, right, to see, well, what does it mean? What do these points mean? Why is their position, why is this position way out here? Well, this point here, it's unusual. It's referring to a point that had a very high January temperature, I know that much, and also the housing value is really big as well. So maybe that means something to me. Okay? So that's sort of what we're trying to get at. I guess, I don't care for much for those 3D plots. We can't help it. All these. So how do we work out? How many axes to choose? One way would be to choose those axes with an eigenvalue greater than 1, right? Assuming that we're working with a correlation matrix. Well, all of the first 5 had an eigenvalue greater than 1, so we would choose all of those at least. Another way to do it would be, what you want really is a few axes that are explaining heaps of the variation, and then a sudden drop, so that the remainder explain very little, right? So if that occurs, what you would see would be, some really big eigenvalues, and then it would suddenly drop, and you'd get this elbow in the plot, right? You'd have something like this. Let's say this is the eigenvalue. I'll call it E here, and this is the PC1, PC2, PC3. Right? Here's the eigenvalue of PC1. We know it's decreasing. Here's PC2, also explains a lot. PC3 explains very little, and neither do the remaining ones, right? So you get this. What you're looking for in a scree plot is basically an elbow, where suddenly you're going from high to low, and everything flattens out. And then you say, okay, well, the first 2 eigenvalues explain a great deal, and then it dropped down. This is the same sort of plot, the amount of variation explained, right? I could look at each axis individually, or I could look at the cumulative amount of variation explained. If I was to look at the cumulative amount of variation explained, let's say this is in PC1, this is PC1 and PC2, this is PC1 and PC2 and PC3. You see how it leveled off here? So adding PC3 didn't help much to the amount of variation explained. So once again, you look for that sort of sharp elbow in your scree plot, and that would show you how many dimensions to choose. Right? It seems this is a very arbitrary way, right? Because, what's an elbow? If we look at this, is this an elbow? Not really. Here, obviously, you're not going to choose 3, but you might choose 4, you might choose 2. It's subjective. But if you're lucky, it's going to be obvious. Right? And that's what most people do, in all honesty. They look at the scree plot to see, well, how much variation is explained by the inclusion of additional axis and additional axis. Okay, so that kind of explains the key parts of the non-computer exercise. You can also do this prac.pain exercise if you've got time. I won't go through that right now. So, how long have I got? I could actually just use my slides. I didn't realize. Okay, I'll go through a little bit more on the slides before we have lunch. Pollution data set, right? It was attributing pollution across the US. We had regional climate pollution and demographics. This is your scatter plot matrix. So this is your, also known as your draftsman's plot, remember? And it's very complex, isn't it, with 15 variables. It's difficult to describe what's going on. Right, what we've found is we can find the eigenvectors. Right, that first eigenvector, E1, or pollute1, as we've decided to call it, was basically a linear combination of all the original variables. And this is actually the linear combination. These are the coefficients that telling us how we actually combined the original variables. Same thing for E2 all the way up to E15. So if we want to actually project those data points along PC1, PC1 is equal to the coefficient negative 0.345 times the original precipitation value minus the mean of the precipitation value. So remember, the data have been centered. So basically, this whole thing in the brackets is the number of standard deviations the original data point was. So this is the standardization here, right? It's just being centered by the mean and divided by the standard deviation. So this is how many standard deviations the first observation was away from the mean. This is the number of standard deviations the first observation is away from the mean of that variable, and so on and so forth. So if you want to project it into your PC1, this is the actual full equation to do, right? Including the standardization. All right, so your PCs, your principal components. When I say a principal component, I just mean your eigenvector, turns out, same thing. They will simply be a linear combination of the centered data, right? If your analysis is done on the variance-covariance matrix instead of on R, right? If it's done on your, R is your correlation matrix. If it's done on R, you don't have to worry about this step here. So this is basically showing you how the original data variables relate to PC1 and PC2. Okay, so the further you are away, so we know housing has a very strong, it's strongly loaded with respect to PC1. Density is not particularly, it's quite close to 0. January temperature is also close to 0 with respect to PC1. Right? So we can see these things, that housing is important with PC1, but not really with PC2. Right? So points that are projected onto this new basis, if they're over here, they have big housing values, right? If they're up high, the housing doesn't inform us about that, but January temperature does. And so on and so forth. Okay, so the idea of a biplot is what we're going to do coming up after lunch. A biplot is when we are trying to show both the variables and the original data in the same space. Right? The PCs, the principal components, are a linear combination of the original variables. We can project those variables into the PCA space. Right? That's exactly what we've done here. That's the original variables in your PC space. Okay, so we don't have to worry about that. So projecting an object at right angles on a variable approximates the position of that object along that variable. Right? The length of the projection arrow, so that would be if there was if these were arrows, if these were vectors rather than just points. Think of them as an arrow going from 0 to all of these things. Right? So that's what we're going to produce a plot that creates these things as arrows. Right? Here's the arrow going to density. Here's the arrow going for for housing. Houston, we have a problem. Right? So basically it says the length of that arrow describes how much it contributes to that particular space. Right? So what does that mean? That means that a point, an arrow that is really near the center here, is not contributing to this plane much at all. Right? It may be that that vector is sitting in a different direction to these first two axes, right? Whereas, the longer the arrow, the more that that particular variable contributes to this particular plane, right? So this is the pollution data. We know about this. Okay. And this is what we call a biplot. Right, so we know this is what we're going to recreate. These values down here, so we got new data points. Well, what does it mean? The 58th data point had a very high value of the variable that was describing the percentage of population age 65 or over. Right? We know that average January temperature was in this direction, so values that were in this direction have are areas with high average January temperature. Values in this direction had high average January temperature and probably high values like this sort of thing, and with these particular variables. Right? So we know that things that are in opposite directions are probably negatively correlated with one another to some degree. Right? Yeah. You can see that this arrow here, population per square mile, it's very, very small, so it actually has very little effect on the first two axes. Maybe it has an effect on the later axes. Right? Population per square mile. So that has little influence in our plot. Okay, so we're going to take lunch now, and afterwards we are going to look at our movie data set that we have created and see if we can make some sense of that. Tom, so an hour for lunch, say, well, maybe an hour 15 for lunch? Okay, 15 minutes.